The title of this talk is Cost-Effective Large-Eddy Simulations for High-Lift Aerodynamics. So we will be focusing on the high-lift aerodynamics and probably the high-lift prediction workshop 5 case. And I would like to acknowledge my co-workers and co-authors. Aditya Gate, I believe he's online also. Jordan Angel, Cetin Kiris, and Manlang Wang. If I get 1 second to move some windows out of the way, I think I can. Okay. Okay, so the outline of my talk is I will have a short introduction section with motivation and some numerics on the newly developed wall model LES solver we call volcano scales. And then I'm going to, as a prelude, I'm going to highlight case 2.4 from the IAA High-Level Prediction Workshop 5. That's a free air case. And then case 3 from the High-Level Prediction Workshop supposed to come up with wind tunnel test from NASA National Transoceanic Facilities and TF for 5.5 and 30 million grid points. And but it kind of did not arrive, and some of the issues with wind tunnel. So all those wind tunnel simulations were free air, no wind. All those case 3 simulations from the highly prediction workshop were pretty much like without wind tunnel data and CFD to CFD comparison. So later we actually run some of the internal simulations, and I'm gonna focus on mostly on this in terms of how we can improve the grid topology. And if someone really want to have internal simulations with wall model LES, that's almost impossible without certain strategies. So I'm gonna talk about that, and I'm going to compare the integrated loads with CFD versus wind tunnel data, some grid resolution studies. And then I will have some short analysis for the high alpha case that where maximum lift 18 and 19 degrees. And then where the low alpha, where the flap dominant flow case, that's alpha 6 case. And then I will give some summary in terms of where we are for Cartesian octary grid and wall model LES for the scale resolving simulations. Okay. And so, as I mentioned, objective is like how we can expand larger simulations, day-to-day runs for industrial research and development. And we are not really saying that you have to run LES for every cases. And in the picture on the left shows that the hash section, conventional CFD is valid for this. When airplane development, airframers use this graph for operational purpose, like the cruise condition where flow is steady state, maybe RANS has been validated, and it may be valid for like a modeling is representing the physics, and we really don't want to touch that. But outside of the curve, flaps down and up, like during takeoff, landing, buffet boundary, maneuvering, all those require like scale resolving simulations, and it becomes really time consuming to get those. How can we democratize this portion of CFD and make it possible to, less cost, robust, fast, and predictive? That's the target. And I give an example of the high lift aerodynamics in a separated flow. And we will be talking about high lift aerodynamics only, but maybe as a additional information that has been validated for high alpha aerodynamics, ice wing aerodynamics. We also have strong, presence in the some cases with shock-induced boundary layer instabilities that could be, it could be rockets, hammerhead type, or or it could be um, the shock bundler interaction on the wing. There is also a strong need for LES on engine characteristics, noise, and installation effects, and as well as the electric vertical takeoff, landing, eVTOL. It requires this type of simulation for to get the aeroacoustics prediction. And then the argument we have is all those simulations, it's completely doable if someone has DOE-like supercomputer or larger number of GPUs from a cluster. Um, but it doesn't really help to many people to come in. The high performance computing queues become crowded, and everyone is saying, "Oh, we need more compute power." And our goal is, can we move that to some consumer grade, like a much less resources, right? We don't expect industry to use top 10 supercomputers such as this DOE mission. And some examples I will give is like either 8 node A10G from AWS, or we currently have a couple of those one node L40S with 8 GPUs. Also, many runs can be also run in workstations, 2 RTX 4090 GPUs. And we are not against the HPC. You can actually run those to HPC clusters if someone has access. But instead of running one case, if someone can run 10, 20 cases simultaneously with less resources, that's actually the goal, right? And also, I'm going to relate that to CFD Vision 2030. So this is kind of IC at AIAA technical committee, and the idea is before we reach to 2030, like CFD has to come to a place, and engineering or scientists must be able to, start from CAD, generate all the pre-processing, um, perform the number crunching, analyze it, interpret, and everything needs to be done like in a short time, like a 24 hours. And that's where the CFD would like the community would like to see. And there are a lot of like problems, like grand problems, grand challenge problems. One of them is high lift. Others are like engine and maybe installation effects. So with the vision elements, I don't expect to read all those vision elements, but it's basically it's accuracy. It has to be the model accuracy. If this CFD tools are not accurate, then we don't really care how fast it is, how automated it is. Once we pass the accuracy, we really like to have a robust automated workflow, because that will reduce the turnaround time for the CFD technologists, and then really cost, like how fast it can be, and then what it costs, like in terms of dollar value or energy utilization. Once we have all those three swim lanes really uh, like optimized, then we can talk about integration. Integration is like a multi-disciplinary analysis, optimization. Really, I mean, if the single discipline is really struggling with accuracy, automation, and cost, then it's going to affect other disciplines when you try to integrate. And our goal is, as Bernard said, I had exposure to many grid paradigms, Navier-Stokes, Lattice-Boltzmann, and all those. So the dream is really, how can we um, like optimize the workflow? Number one is we have to deal with this efficient automated meshing paradigm. And I am proposing as a Cartesian octary, not only like uh, in terms of generating this quickly, but also it gives ability to do grid resolution studies in a very short time, and then you can do simultaneously good resolution studies and then check mark this verification process in a couple of days instead of multiple months. And then of course, memory efficient, low cost computing, everything we design is the code is compute bound, is not a memory bound. So that's why we are utilizing this consumer grade GPUs. Okay, the volcano scales is the product for our wall model LES, and then the core philosophy is again, as I said, as I mentioned, LES is day-to-day production with predictive, fast, and cost computing. The capability is really like it may change from problem to problem, but to our experience, in 2 RTX 4090 with 24 um, gigabyte memory, 500 million cells you can run. Maybe a couple of hours, maybe overnight, depending on the problem. This highly prediction workshop case, AWS A10G, it has been used, and you can run like a 1.5 billion cells. And our current machines on the L40S with 8 GPUs, you can run like a 3 billion cells. So um, doesn't mean that um, you know you can use MPI, which that version is coming this summer, and you can run multiple nodes. So the idea is to make the code fast. So the total GPU hours as small as possible, so if you want to decrease the turnaround time, you can have multiple blocks, but at the end, it's a zero-sum game. Whether you use one node or 10 nodes, total GPU hours are same. But if you use 10 nodes, then you will get almost 10 times less turnaround time. And then um, so I think I kind of gave the idea for this case. So the idea is don't make this hero calculations. Bring it to day to day to your workflow. And then the other thing is really machine learning AI is another area that they need fast, accurate, and rich data, right? So machine learning, if needs that data, then we have to make this really fast and accurate. Okay, and then the one page I have on the what's the numerics and the models. So as I mentioned, we have wall model larger the simulation solver, the no, name scales. Focus on GPU acceleration. So far, it's all NVIDIA CUDA base, and then we actually use immerse boundary description of the geometries on a Cartesian octary grids, and we use fully compressible Navier-Stokes formulation and no dissipative spatial discretizations. And many of you might be familiar this kind of methodologies in wall model LES. And highly prediction workshop, almost everyone use similar wall model LES options, which explicit SGS closure. It's available like constant coefficient Riemann, but we prefer to go to dynamic Simoguinski model to remove the dependency on the co fixed coefficient. And since the grid is isotropic, it's perfect for explicit time stepping. You really don't need implicit time stepping for robustness purpose. We have no transition treatment. It's an issue for many wall model LES, but it's completely numerical discretization controls the transition. And we have algebraic equilibrium wall modeling, and also we have tested the numerical scheme. It's a all Mach number formulation, and that's to our experience, it has no problem in terms of robustness, like a Mach point 0.1 for automotive to Mach 6 re-entry capsule we tested by ourselves. We have some users, they tried Mach 8 and they seem like they have no problem with it. but that's something we didn't have a hands-on experience going beyond Mach 6. And then the next maybe 5-10 minutes, I'm gonna focus on the reminding free air case from Highly Prediction Workshop 5. That's case 2.4. It's kind of a prelude to internal simulations. So, I think if you haven't had any chance to reach like a AIAA paper from SciTech, summarize all those cases, that case 2.2, 2.3, 2.4, and basically in the wall model LES TFG, some participants submit those, and then Neil Ashton, he used to be at AWS at that time, he ran those cases. And the key question from the wall model LES TFG is really, can we get within a 1 on 2% error at CLmax? So that's actually another criteria for certification by analysis, CFD 2030. The whole community was looking for it. It's not only the question for wall model LES, it's a question for RANs and hybrid RANs LES. And the other thing I try to push is there an evidence of grid convergence? And what's going to do at the flight Reynolds number? Like this test case was 5.49 million Reynolds number, and then the goal for case 3 is 16 million and 30 million Reynolds number based on main aerodynamic code. And then the other one is the prediction is industry friendly. Like, do we need like a computer grid, or everyone supposed to do their own grid generation? And how does computational scores compare the current industry best practices using RANs? So um, based on that, I think I was able to give like a summary paper of the entire wall model LES TFG, but Neil Ashton presented scale submission in this paper number 0888. And I suggest to maybe to read the paper and read. There's a lot of detail in that paper, and I'm just gonna summarize what he submitted in 2.4. So before that, I like to touch a little bit on the workflow. So with volcano scales, and please, this is not an advertisement, that's just explaining what the process is. In the pre-process, we really don't do anything with CAD model, but if we have the computed CAD model ready for CFD, like that could be native CAD model, IJS, BREP, step, or if the user has an STL file, it might be an old model. The mesh generation can start immediately. In a couple of minutes, you can run billion volume mesh, the surface mesh that required for billion grid points for volume. And then automatically based on users input, volume mesh is also generated in terms of 5 to 8 minutes for multiple billion grid points. So the idea is do not start with fine grid. Always start with coarsest grid you can. And after the grid generation, you run this in the system, the GPUs you have access. It could be, two RTX 4090 type, excellent machine for debugging, or if you have HPC access, you can run it. And one thing with Scales provide is post-processing. It's not only visualization, it's like a point sensor, surface, whatever information you are looking for. There's an intuitive post-processing that you can see or analyze what you are computing, and that will give an information to, if it's a high-lift system, aeronautical engineer, CFD scientist is familiar with the flow. And for example, if that chine vortex, if CFD technologist doesn't see it and aware of that kind of thing, they can put a block and come back to where they stop and add that block, and solution is interpolated from previous case, and then they can he or she can continue running. So this whole thing may take like 3 to 5 hours, um, optimizing the courses grid. And once you have the courses grid, you don't change relative resolution between fine grid section and coarse grid section in that optimized coarse grid, and you change one line of input parameter, that is minimum delta x. So you can start doing grid resolution studies by changing minimum delta x. For this case, it's a 5 millimeter, 4 millimeter, 3.2 millimeter simultaneously, and that's actually very you know difficult process with non-isotropic and non-automatic grid generation. But with Cartesian octree, this can be done very easily, and it removes this verification question whether I am solving my PDs correctly or not. And it's an example that Neil has done. And Neil, as I mentioned, currently at Media now, but he submit these cases. So, and also, he's not working for an airplaner. So he's a perfect CFD background, but not like an aeronautical engineer type designing airplane. So he started very simple, um, a methodology that, hey, I'm going to select the wing suction surface as my finest resolution, independent of your minimum distance, right? Coarse grid. And then the second finest is going to be orange. The third finest is going to be green. And then fourth finest is going to be like a purple. So I mean, he ran this coarse grid simulations that's 5 millimeter minimum distance. That's for case 2.4, that gives him like 436 million grid point. And the slice at y equals 25, that fine grid is shows like a delta x, right? And then in his coarse grid simulations, he noticed chine vortex, the some wake coming from slats that creates pizza slices, and maybe flap separation, and even maybe the effect of the wing to the horizontal stabilizer could be an issue. So he created a volume refinement regions. That's a very simple geometric shape. And then he finalized his coarse grid topology. And then he ran coarse medium fine. That's 436 million, 678 million, and 1.05 million, with the 5 millimeter, 4 millimeter, 3.2 millimeter minimum spacing. And these are like a flight scale model spacing. And then this is I am pretty sure some of you already saw this, because it's a 1.5 year old video. But it shows like a fine grid simulations, angle of attack 23.6. This is case 2.4. Really, like, things to be taken from this is, if you do not resolve turbulent quantities, the inboard separation is being affected by the chine vortex, and the pizza shape separation is being affected by the slots, and transition is another thing. And even like a flap separation plays an important role. Horseshoe vortex during this junction. Like, if you don't resolve all those details with High-Level prediction workshop, you may actually get good results in the integrated quantities because of the cancellation error. But if you do like a CP cards and all those, you notice like you're missing something, right? So we don't want that to be really have a lock that error cancellation gives you a good lift and moment. We really rely on one model LES we have is really not relying on any coefficients or anything. As long as you have space-time resolution, you'll get some grid convergence, and maybe modeling errors still can be due to the wall modeling, but you don't rely on anything else. And when Neil ran those cases, he also noticed that in wall model LES TFG, like a lot of wall model LES groups were not sure how the transition occurs, and as I mentioned, there is no transition model. So the best way is to reduce the minimum spacing. So he did like without changing to number of grid points too much based on those grid resolution studies, he reiterated his grid topology, having 2.2 millimeter minimum, but then second level is 4.4 millimeter in the suction side. And I am giving like a, surface mesh is about 2 minutes, and then surface to volume mesh took like 8 minutes for this case. It's just single node of the AMD machine, right? And then case 2.4, I am giving some timings here. Um, conditions are given like angle of attack is 7.6 degree to 23.6 degree. And so the timing for fine grid is 1.05 billion. When you run on 810G, it's like 2 hours per CTU. CTU is like a based on mean aerodynamic code. And then if you bring that to L4DS, that's almost half of it is 1.08 hours. And best practice grid is slightly lower than fine grid. That's 1.02 billion, and minimum spacing is 2.2. The wall time is 2.75 hours, and in 810G, and then 8X, 8 GPU L4DS is 1.48 hours. It's more because it's an explicit code, and when you have smaller delta X, you have to go to small delta T. So the number of wall time per CTU becomes larger in that case. But in terms of the another thing I like to bring, that if you start with free stream, the total turnaround time on A10G is 88 hours. And if you put in a dollar amount, that could be around $1,000. And with the fine grid, that was around $800 or less than that. So with the auto sequencing, that means you start with a coarse grid, you get rid of the numerical transient, and then refine your grid to second level and third level. And then you end up really running the fine grid much, much less amount of time to require, like you need the averaging. That takes 29 hours, and the approximate cost of it is $377. Um, and then the grid convergence study, these are all blind comparison. So the Onera wind tunnel has not been released to the participants or any TFG leads. So the gray, the grid resolution studies is red is the coarse grid, medium and fine grid. So coarse grid is suffering quite a bit. So the outcome from entire TFG is like at least you need like 500, 600 million grid points to get a reasonable CL max and pitch break. And as you see, like a green and orange, the difference is not much in terms of for an engineering purpose. Neil and the volcano team helping him find that it's a good solution, and with the blind submission, when the comparison has been done, that was really satisfactory for the TFG wall models TFG, that this can be done. So we answer some of the key questions that way. And then and then the when you do the best practice grid, I don't have time to explain, but paper has a lot of explanation on that. So best practice grid is still good comparison, but CLmax get lower, and but it eliminated a lot of error cancellation between inboard, outboard, flap. Um, so CP cuts actually makes more sense in the best practice grid, but uh, it removes this error cancellation, and then CL max get still it's in the um, bracket that the solution is acceptable, but its fine grid solution was better, right? And then this is like a CP at 19 degree. Um, Again, 2.4, 5.5 billion Reynolds number. And, workshop requested to submit CP cuts on these lines, like ABC are inboard, DEF are midboard, F to J is outboard. And I'm kind of showing best practice grid on row A through I. Um, it's 19 degrees is actually pretty good. There are maybe a little bit underestimation on the flap on row G. Other than that, it actually gives a very good comparison. And at stall 23.6, again, row A through I, and row G still sees some flap issues, and as well as row E, there's an underestimation, but that was actually uh, true for almost every CFD submission in the highly prediction workshop one. And then scale versus oil flow from Onera. I think the biggest thing is like is CFD can predict outboard those size of pizza slices, and then what is the size of this inboard separation? As I mentioned, there's a lot of factor for that, like the volume refinement, the chine vortex affecting, and if you don't have a right inboard outboard separation, then you really don't do well as a CFDer to predict this. And this shows actually a very good comparison. Okay, and then internal simulations, I'm going to go a little bit quickly. As I mentioned, like the idea is to bring case theory data to CFDers during the workshop from NTF. NTF is NASA National Transonic Facility, and there was no really intent to do internal simulation. Everyone did like a free air simulations, and I'm actually borrowing this slide from Chris Ramsey's committee summary presentation at the high lift prediction workshop conclusion summary. And he actually showed some preliminary, so I think NTF was having some um, mechanical issues. I don't know the detail of it, but wind tunnel data never been released. But there were some issues in terms of the Onera wind tunnel data versus uh, the NTF data. This is like a Reynolds number, even Reynolds number, moderate Reynolds number. There was some delta between the two. And then free air, wall model LES, all those black symbols, they were somewhat close to Onera data, and the question is, what's really the cause of that delta and why NTF data is lower? So NASA TQ project actually tasked some researchers, and we are one of them. They ask us to perform in-tunnel simulations for Reynolds number 5.49, 16, and 30 million. And then we have done a good resolution studies, 5.4, 3.25 millimeter. these are based on full scale model, those delta X's. And then later, I think we are going to be performed toward this end of the summer 2.6 model that's a full span. What we did is a half span simulation. And this is kind of shows the CFD run metrics. And we performed 5.4 and 30 million. Data was not available for 16 million, but we still performed those. Every case has medium course uh, and wind tunnel install fine, but also we perform same delta X minimum spacing for medium free air, so we can compare. And as I said, delta is provided by NASA Langley, and those coarse and medium runs were executed on a single NVIDIA A10 node. That's a NAS machine, NASA Advanced Supercomputing, 4 GPUs each. So we were able to span all those runs simultaneously using one node instead of asking more nodes and waiting in the queue. It was extremely efficient that you can grab each node very quickly from the PBS queue system and then perform those in a week time frame. We actually did 24 each, so it just took this whole thing took less than a month to complete entire 78 runs. Okay, and then optimizing grid topology. I think I'm getting a little bit behind my time, so it's the same idea. We did some free air. Basically, we want to improve the volume refinement with Topo V and like level 0 to level 5, it's 130 million to 1.124 million grid points. And when you do alpha 6, there is not much difference. Alpha 14, there is not much difference. When we go to alpha 19, topology B with the much finer volume refinement does much better job, and it goes to converge quicker than topology A. Topology A is a highly prediction workshop 5 grid topology. So, and it doesn't really add a lot of number of grid points if you look at it, the difference 1.1 billion versus 1.2 billion. So we decided to go topology B, and also it shows, you can actually look at those total integrated as well as the component like wing, fuselage, slat, flaps, nacelle pylon, and the drop in the slat lift shows with this some refinement, slat boundary layer is resolvable with this 3.2 millimeter, and it becomes turbulent LES. So that's also confirming that we really didn't have too much issues in the highly prediction workshop 5 for the transition. Some people, some submissions suffer more than scale submission. And this is also shows um, what's causing on the bump, like a bump on the 5 millimeter resolution in the CL. Um, the um, the L5, that's a like there is a volume grid refinement removes this spurious boundary layer, and then that um, the finer grid on the chine vortex actually controls and that's actually much better improvement if you want to continue this. So, and then the other thing is NTF simulation. And when you go to NTF simulation, I put some pictures from the NASA website. It's a the idea is to have a cryogenic fluid that increase the Reynolds number but remove the wall effects. In order to wall effects, this is a semi-span. All other three wind tunnel walls has some slats, some opening, very tiny opening to reservoir. You are seeing here, and it's really have very wide range of scales. Like the scales near the test article is way smaller, but if you really want to resolve, if you want to include that installation effects, the the tunnel dynamics takes forever to settle down. You specify the back pressure, and that creates waves, and that waves travel so long to come back and forth. And if you really want to do like the way free air does from free stream, it's impossible to have this turnaround time with a fine grid. So in order to do that, we decided to go some grid sequencing. And first, we actually applied that in the free air case, like 1.26 billion grid points. We ran free air case like from free stream initialization. That's a blue color here in the CL plot. And then the other simulations we did is we started with 323 million grid points free air, and then we stop. We get a grid sequencing. We interpolate solution to 1.2 million grid points, and then we started, and it reached to level that free air simulations from initialized from free stream. It reached to that level, and we got that confidence, so we moved to internal. So internal, for each angle of attack, you have to define a different P exit. So there is no unified exit value back pressure that it will work for all angle of attacks. So for that, we have an automated PID controller. And with this grid sequencing, we can reach to that equilibrium in the wind tunnel very quickly. And then next slide, I'm going to show that, right? So there are like a 3 precursors grid before we actually get um, averaging on the baseline grid, I call. And lowest average on the baseline grid, like about 10.1 to 10.35 seconds. I'm showing here CL, and so this, and then there is a target Mach number. There is a sensor upstream of the test article. So target Mach number has to be 0.2. So the idea is with this orange grid, the curve shows orange. That's 21 million grid points. It's a very coarse grid, and you run that for a long time. 6 seconds is, each CTU is 0.05 seconds, so it's a lot of CTUs. And then you make sure that you reach to equilibrium in the wind tunnel dynamics, that your target Mach number is 0.2. Then you actually refine grid to 355 million in the test section, that you try to resolve the tunnel floor boundary layer. And that's run like about 4 seconds. And then once you get like once you resolve that, you go to next grid level. That's about 1.07 billion grid points. That's you run very short time to have like a test section slot mass flow stabilize. Like the chamber versus test section, you have inflow and outflow through those slots. And then after that, you go your baseline grid, 1.4 billion grid points. You run it like 0.25, 0.3 seconds, about 50 CTU, and maybe last 20, 30 CTU or 40 CTU, you get averaging, right? So that's the idea. And the timing in terms of using for a 100 total GPU hours span is precursor A is 2 hours, 2 total GPU hours. That means 30 seconds you can get this 6 seconds, right, turnaround time. And the total GPU hours for this case is 750 hours. Again, that's not a turnaround time with 4 GPUs hour time. You can get this in about a week using 4 GPUs each node, but you can do this simultaneous, and you can do entire thing using, if your angle of attacks is 8, And if you are doing 3 Reynolds number, 24 case, you can run in 24 different nodes, get the whole thing in 1 week. And then in a precursor A, 21 million grid points, I'm showing two cuts, like a X constant cuts and Y constant cuts. And it's kind of showing the flow field, right? The whole idea to get this orange and then get target Mach number. So we really don't care about resolving the geometry. It's like it's barely represented, just a drag object. And grid resolution is not allowing to have in and out between the slots. But when we go to precursor V, that's a 355. Oh, by the way, over here there's only 7 points across man aerodynamic chord. So you don't see the details of the test article. And then precursor B used 357 million grid points. It has 110 points across mean aerodynamic chord. X constant section, you see slots can be now represented. It's not good enough, but it can be. So the whole idea to represent boundary layer on the tunnel wall, and usually you need like a 10 points per boundary layer thickness on the rake, and model again represented slightly better. And precursor C, the whole idea is focusing the dynamics between test section and chamber through these holes. We put at least 18 points, and that's the circle shown here. And that's model is reasonably resolved, 1,000 points across my aerodynamic code. And then the last is the final grid, 1.4 billion grid points. Definitely we have much better interactions. So low momentum fluid pull from the plenum due to angle of attack, and high momentum fluid push into the plenum. The sufficient resolution capture of all whatever vortices. So we actually submit this data to project management at NASA, and that shows the grid sizes in each section, and that also shows like empty tunnel calibration, like there is a wind tunnel Mach number, also the boundary layer with the wind tunnel wall boundary layer with the model inside, and the target Mach number. We all compare that before our simulations. And then integrated wall is like really lift, drag, and pitch moment. I am showing here coarse, medium, fine. Solid lines is 5.5 million, and dashed lines is 30 million Reynolds number. And I'm not showing an experiment. It's showing the grid convergence study for two different Reynolds number. And medium and fine grid, as you see, produce essentially identical loads. Coarse grid definitely missed the CL max, and clear offset in the lift and drag and pitching moment with increasing Reynolds number. So Reynolds number 5.5 is different than 30 million. And when we compare with the data from NTF data, the offset in the pitch moment more pronounced on the low alpha, right? So we really don't know why this happened, but we observe in the highly prediction 4 and 5. You have good CL agreement up to 16 degree, and then CL max, for converge CFD is like gives a value 2.5, but wind tunnel gives 2.4. And pitch break is observed almost similar to wind tunnel data, that's 19 degree. And this is for Reynolds number 5.5. When we go to Reynolds number 30, it's definitely there is an offset between CL, between scales resolution and wind tunnel data. There's a good agreement in pitching moment, but we are kind of thinking this could be due to error cancellations. And CFD results get CMY correct, but overpredict CL, right? So, I mean, the idea for why we are overpredicting CL, definitely there might be situation that there is in the CFD modeling, there is something we don't model what's happening in the tunnel. And that could be like we are doing a stiff geometry, maybe for this high speed case, the wind tunnel test article deformed a little bit, and it's seeing like zero point 0.5 to 1 degree less angle of attack. That could be one reason, but until it's verified, we don't know. And this also shows a Reynolds number effect that um, the scale shows monotonically increasing lift and decreasing pitch moment. Um, but CL from the wind tunnel data shows essentially no sensitivity to Reynolds number for up to 16 degree and more nose up moment for high Reynolds number. That's opposite the CFD, but both scales and CF experiment predict pitch break at the same angle of attack for both Reynolds number. So, I mean, it's partially good. There are some discrepancies, but there's also discrepancy, as I mentioned, between Onera wind tunnel and NTF wind tunnel. So we actually, our CFD created some maybe questions that it could be in model deformation or it could be something else. So I think I am reaching um, to end of my time. Bernard, shall I stop here and go to conclusion? And
As you
or
were setting, if you have, I mean, we started 5 minutes later also, so you can take those for you.
okay, in that case, I will go a little bit quickly. I will touch the main things like we also, as I mentioned, we run a free air case with the same medium grid resolution, and we compare that with two Reynolds number 5.5 or three Reynolds number 16 and 30 million. So solid lines are the install case and dashed lines are free air case. So the takeaway is the stall occurs 1.5 to 2 degree lower in tunnel simulations than free air. The CL sensitivity is low on low Reynolds number. In tunnel CFD shows substantially lower drag compared to free air, and essentially more nose up moment observed for internal CFD compared to free air results. And then I think I'm going to go very quickly on those high alpha case to show like for Reynolds number 5.4 alpha 19, basically the inboard separation, no side body separation for free air CFD, but there is a side body separation on internal CFD. And when we compare the skin friction, free air versus internal side by side, you see that large wing root separation for the internal. This is a free air case. And in terms of Reynolds number sensitivity, alpha 18, there's a clear reduction in the pizza shape outboard separation as you go from Reynolds 5.5 million to 30 million. Flap separation doesn't appear to be very sensitive. And again, this will be in the paper in SciTech 2026. Because of the time, I really don't want to drag and I want to respect your time. So these CPs are compared with different grid resolution, inboard, a midboard, and outboard. Basically, the fine grid shows nearly perfect agreement in many places. But there is definitely some discrepancy in this slat. Even though you use fine grid, flap actually agrees very well when you go to the fine grid. And then this is a 30 million case, and same idea, like there's an over prediction in root area than row A, and medium and fine grid comes out of asymptote, but it's higher than experiment. So this CP picks between CFD and experiment is kind of an indication also, and it might be due to angle of attack difference 0.5 to 1 degree between CFD and wind tunnel. Maybe wind tunnel test article deform slightly. That could be a reason, but it's a kind of a guess right now. It needs to be verified. And then the same story, I don't want to drag, and whatever I say here, actually I said during the talk, so I'm not gonna read that, but that will be probably in the recorded, and people can stop the movie and can read it. And then alpha 8 is the same story, and we have the CPE cuts. Again, it's an indication that as you see, alpha 630 million. It's a slat and main element, shows some difference, and that's again 0.5 to 1 degree offset on the angle of attack. That's our conclusion for this study, and we have been communicating maybe the experimentalists, if they do that again, scanning the geometry, how much it's deformed, might be a good thing to do. Okay, and these are the conclusions, pretty much similar. The we show a good agreement, but uh, there are some discrepancy. And then the summary in a big picture, I think we kind of demonstrated Cartesian octary grid paradigm could be very appealing with these three aspects. One is the automated and very efficient grid generation. And the second is the LES-friendly discretization, the higher order finite difference, and energy entropy consistent scheme became popular. Many immersed boundary we are seeing, and everyone has different way of tackling this problem, but it's becoming popular. And because grids are in excellent quality, we don't have to use implicit schemes. We use explicit. And also the third aspect is it's exceptionally GPU friendly, as I mentioned. We have a compute bound, and because of that, you can actually run consumer grade GPUs instead of more expensive GPUs. Doesn't mean that we cannot run, but you pay less hardware money if you run on the RTX as L40. With that, I want to conclude it. I apologize, it took a little bit longer than I thought, but I'm happy to answer any questions if there are any questions, and if we have time for some.